Free fall of two stones. Two stones are thrown vertically upward from the ground, one with 3 times the initial speed of the other. Part A. If the faster stone takes 10 seconds to return to the ground, how long will it take the slower stone to return? Part B. If the slower stone reaches a maximum height of capital H, how high in terms of capital H will the faster stone go? Assume free fall. Okay, so we have two stones. One has an initial speed vi, the other one has an initial speed 3vi, 3 times the initial speed of the other. They're all thrown vertically upward, and the faster stone, which is stone 2, takes 10 seconds to return to ground. So for stone 2, I can write its velocity v2 as a function of time to be its initial velocity 3vi, because this is my y-axis, so it's in plus j hat direction, so it's positive 3vi, and there's gravitational acceleration g pointing down, so we have 3vi minus gt as our velocity as a function of time. If I were to plot this velocity as a function of time, what would I see? v2 as a function of time, it starts from 3vi, and then it goes to minus 3vi when it reaches the ground. So I will see that it starts with 3vi, and then it will come back with minus 3vi, and this is completely symmetric, so it will go to a height h, and then it will travel the same distance h, so that the net displacement delta y will be h minus h, which is 0. So finally, when I finish this travel, v2 at time of flight is going to be equal to minus 3vi, and which is the initial velocity 3vi minus g time of flight t final. So I find that for the second stone, the time of flight is basically 6 vi divided by g, and this is equal to 10 seconds. Therefore, I find that vi divided by g, gravitational acceleration, is 5/3 seconds. Okay. Now, for stone 1, I can write its velocity as a function of time. v1 as a function of time is vi minus gt, and similarly I can basically say that v1 at time of flight of the first stone will have reached a velocity minus vi, so this is vi minus g time of flight for the first stone. So this will give me time of flight of the first stone to be equal to 2vi divided by the gravitational acceleration g, which is 2 times vi over g. So vi over g was 5/3, so it is 2 times 5/3, 10/3, and I see that I'm given one quantity here which has two significant figures, so I will report my answer in two significant figures. So the time of flight for the first stone will be approximately 3.3 seconds. Okay, and now in part B, so this was my part A, maximum height uh, I call capital H, and you can remember that the slower stone reaches the maximum height capital H, so I'm calling the maximum height H, the maximum distance the first stone will travel when going up, and so that's the slower stone. So this maximum height will be achieved when dy dt is 0. So that means I have the velocity, instantaneous velocity of stone 1 equal to 0. So delta y maximum is h. This is the integral from time t equals 0 to time t prime. Its velocity is a function of time, vi minus gt dt. So this is the velocity of the first stone as a function of time. So I find that this is vi t prime minus g t prime square divided by 2. So I know that the velocity at time t prime, which is vi minus gt prime, must be equal to 0. So t prime, the time it takes to reach the maximum height, is vi divided by g. So I substitute that for t prime. So I find that this is vi square divided by g, so vi times vi over g, minus g over 2, vi over g parentheses squared, so vi squared over g squared. I see that this g cancels this g, and I'm left with vi squared over g minus vi squared over 2g, which is vi squared over 2g. And this must be equal to capital H, the maximum height achieved by first stone. Now for stone 2, with the faster stone, maximum height will be reached when its instantaneous velocity v2 is equal to 0. So at that instant, v2 at time t double prime, I have a velocity 3vi initial velocity minus gt double prime. This is equal to 0. So that time t double prime is, in this case, 3vi over g. So the maximum height that I'm going to reach, delta y maximum, is integral from 0 to t double prime, the time when it reaches the maximum height. Its velocity v2 is a function of time, 3vi minus gt dt. When I do this integral, I find 3vi t double prime minus 1 over 2 g t double prime square, and I substitute for t double prime 3vi over g, so it is 3vi times 3vi over g minus 1 over 2 g 3vi over g parentheses squared. So the first term is 9vi squared over g. The second term is 9 minus 9vi squared over 2g. So this answer is 9vi squared over 2g. And remember that vi squared over 2g was capital H. So this answer, 9 times vi squared over 2g, corresponds to 9 times the height h. So the answer is 9 capital H. Okay. So let's review what we did. We have two stones that are thrown vertically upward. Stone 1 with initial speed vi, stone 2 3 times the initial speed of the other, thrown vertically upward. The faster stone 3vi takes 10 seconds to return to ground. So I want to know how long it takes for the first stone to return to ground. And if the slower stone reaches a height capital H, the faster stone reaches what height in terms of capital H. So in order to answer these questions, I need to know velocity as a function of time. For the second stone, where I have an initial speed 3vi, the velocity as a function of time is 3vi minus gt, and because I have a linear relationship between time and velocity, when I go back to the same position, the same area under the velocity versus time plot, plus h and minus h is achieved, and I obtain zero displacement, so I return to ground. That's what it means. With the same speed, opposite direction, minus 3vi. Okay, so plus 3vi, and I come back with minus 3vi. So that is achieved at time of flight for the second stone, which I found, which was given to me as 10 seconds. So vi over g ratio is 5/3 seconds. And then I went to look at v1 as a function of time. Now this is vi minus gt. The same argument applies. Due to symmetry of the vt plot, I have to reach minus vi when it goes back to the ground. And this happens at time 2vi over g, because vi over g was 5/3, that is 10/3, with two significant figures. This is 3.3 seconds. And then for maximum height, capital H, reached by stone 1, which happens when its instantaneous velocity is 0, the displacement on the y-axis, delta y max, is integral from 0 to time t prime, the time when it reaches the maximum height, vi minus gt dt. And because this velocity, instantaneous velocity, has to be 0, I find that this t prime is vi over g. And substituting for t prime vi over g, I obtain vi squared over 2g is the maximum height, which is called capital H. For stone 2, when the maximum height is reached, its instantaneous velocity is 0, so 3vi minus g t double prime is 0, so t double prime is 3vi over g, and the total displacement delta y max from 0 to t double prime is integral v2 dt, and this basically gives me, when I substitute for t double prime, 3vi over g, 9 times vi square over 2g. Vi square over 2g was capital H, so in terms of capital H, this maximum height is 9 capital H.